When we apply the energy principle to understand the motion of a system, we think of states of the system when we examine the change in the system energy delta E. Let's say, for example, in the initial state our system is here. Then, later, in the final state our system is here. When we think about delta E, what we're concerned with here is comparing what happens at these two states. In other words, we're comparing the total energy only at the endpoints, and we typically ignore the values of the energy that the system has in between as it moves from the initial to the final state. However, for energy transfers, we have in general a different picture. The transfer of energy is a process, meaning energy transfer doesn't just necessarily happen at the initial state and then again at the final state, but will typically be happening in between as the system moves from the initial to the final state. In the case where energy transfer occurs via work, the forces involved will generally be transferring energy to and from the surroundings all the way along in between as the system moves. Now, to describe this transfer, we introduced an expression for computing the work done by a particular force as the scalar product of that force with the displacement. And this expression, as written, is fine as long as F and delta R don't change in between. However, if there is some kind of change, say the magnitude of the force changes, or the force changes direction with respect to the displacement, then this expression for the work fails. We need to modify our definition for work so that the energy transfer is correctly described all the way along at all points between the initial and final state. Here's how we can fix this. Again, we imagine that our system progresses from an initial state to a final state. But here we're going to think about the path as being rather curvy, say like this. Now let's think about breaking this path up into a sequence of small displacements, say something like this. Now how do we know what small means here? Here's how. We choose the displacement small enough such that the force we're considering is, to a very good approximation, constant during this displacement, meaning the force doesn't change in magnitude, and the force maintains the same direction relative to the direction of the displacement. So, for example, let's say we have a force F that is not constant along the entire path, but for segment 1 is a constant force F1 and can be represented by an arrow like this. Then, along this piece of the path, the work done by the force F is F1 dot delta R1. Now let's say along segment 2, the force F is well approximated by the constant force F2. Then the work done by the force F along this piece of the path is F2 dot delta R2. We can keep going like this until we reach the final state. We can now compute the work done by the force F along the entire path. It's just the sum of the works done along each piece of the path, like this, which we can rewrite compactly using the Greek letter capital sigma to represent the sum. Let's try using this approach to compute work on this question. Here's the solution. Notice the force of the push is not constant along the entire path. However, we can break up the path of the crate into two pieces, where the force of the push is constant along each piece. Then we can compute the work done by the push along the entire path. Now, if we go to the limit where the small displacements become infinitesimals, then our expression for the work done by the force F goes from a summation to an integral. For delta R sufficiently small, the summation is often a good approximation to the integral. There will be cases we'll consider where we can do the integrals analytically, so it's good for us to know how to do that. In fact, let's now do one such case involving a non-constant force that's well known to us, the spring force. Here's the situation. A spring is attached to a block as shown. Initially, the spring has a length of 40 centimeters. The block moves and the spring has a final length of 10 centimeters. The relaxed length of the spring is 30 centimeters, and the spring stiffness, K, is equal to 100 newtons per meter. What is the work done by the spring on the block as the block moves from its initial position to its final position? Here's a sketch of the problem. Clearly, the spring force is changing magnitude as the spring changes length. Moreover, the spring force also changes direction. It points left while the spring is stretched longer than the relaxed length, but later switches to point to the right as the spring is compressed to a length shorter than the natural length. So let's break up the displacement of the block into small pieces of displacement dr. If we choose the horizontal direction as our x-axis, then this vector integral is just an integral along x, where the symbol f sub s here just represents the only non-zero component of the spring force, the x component. Let's choose our origin such that x equals 0 corresponds to the block's position where the spring is at its relaxed length, L0. Then we can write f sub s as minus kx, where x is equal to L, the spring's length, minus L naught, the relaxed length. Notice that in this problem, the displacement is always to the left, and that the force at the start points to the left too. So the spring force does positive work at first. It transfers energy into the block, which is our system. However, later, when the spring is compressed, the spring force points to the right, so that the spring force later does negative work. It transfers energy out of the block. Until we do the integral, we don't know what the total effect is. Net transfer out or in. So let's find out. Putting in the limits, the lower limit is the initial position, the upper limit is the final position, and we do the integral and we see the total work done is negative. The overall effect of the spring force acting on the block as the block moves from the initial position to the final position is to transfer energy out of the block. A natural question would be, where does this energy transferred out of the block go? To answer this question, we'll need to introduce some new concepts. We'll do that in our next lecture.